All right, so let us quickly end up on our discussion on the fourth module, and that was dealt with the key exchange protocol. So we have done the DH, we have done the L-Gamma on last day's class, the brief class that we had. The last but not the least is what we have is called as elliptic curve cryptography. The E is missing over here. So this is elliptic curve cryptography. And this actually is a process which is very similar to what we have discussed so far, except that in this case, the arithmetic will be in the form of elliptical curve arithmetic. And the points which we are going to consider for key, or for that matter, the generator point, like we had the primitive roots and all, in this case, it will be considered with respect to a elliptical curve. That's the only change. And you will soon find the procedure is almost the similar. We are generating the private key, we are generating the public key, we are multiplying the message to that of the private key and all those stuff. Very similar. But remember, all this calculation will be based on the elliptical curve arithmetic. Okay, so that's the only change. One of the advantage of this is given in the second line, as you can observe, that it is providing the same set of security, but using smaller set of key, as in the table it's mentioned over there. In RSA, you can see it provides the similar security. In ECC, there is a significant change in the number of bits which are going to get occupied for the generating the similar kind of security. In RSA, you need 512 bits for the particular security, whatever you consider. In that case, it is 112. So that's a relatively a drastic change in terms of the number of bits used. Because remember, some point down the line, why it is so important? Because the number of bits, if it is less, in a way you are saving the bandwidth also at some point. And instead of those redundant bits used for the security, you can use more number of data bits in between. So in a way, you are improving the data rate at some point, indirectly. Right? So that is why this process is very much famous in terms of key exchange protocol. So let's see how it is to be done. But for that to come, we need to understand few things. Very simple. And since with the knowledge of CAT2, we already have the elliptical curve arithmetic in there as a syllabus, I don't think there will be much of a problem here. So if you can observe that here also, we are going to use the same equation x3 plus ax plus b, which we already done. In fact, that is the reason we have done x3 plus ax plus b. Because for elliptical curve arithmetic also, we are considering the same equation over here. And if you see the graph over here, this is basically the points, if you consider all the points on a particular elliptical curve, the one that I asked you in one of the questions, in fact, in CAT2. So this is the graph that you are getting, and you can observe that it goes infinitely. So it will go on like this, it will go on like this, and the points reside like P and R, these are the points which are on the curve. So we are not discussing that. One very important thing that we have to understand is something called as N, which is given over here. Alright, so now if we observe here what is mentioned over here, N is called as, it's ideally the order of the curve. We call it the order of the curve, and most of the time it's provided to you. So this is the maximum point or limit to the curve. The points to be tested must be within this limit. Alright, so this is how it is to be, because infinite curves we cannot take, infinite values we cannot take. So we have to take some finite element to it. So that's why this N is sometimes considered. Now, sometimes you will find that the value that the numbers that we are considering, even the prime numbers you will soon find, those all will be considered with respect to the small n. So how we are defining the small n, based on that we are going to switch over the selections. Just like we had for DH or the L-Gamma, we had Q, the prime number. Every time we are directing with respect to the prime number. Same way, this is my limiting condition. So keeping that in mind, the next point that is mentioned over here is why we are using it. So just a simple line, don't need to go much deep in it. The basic reason is that we are doing this. This is also a discrete logarithm problem. Okay, just like the DH and the L-Gamma, we had a discrete logarithm problem. Discrete logarithm problem means it's a trapdoor function. It means going one direction is easy, but the other way we cannot come back. So here also the same thing. Given that we have K, a random value, and given a P over here, we can easily find out what is Q. But on the other hand, if you know Q and you know P, you cannot find what is the random variable K. It's very difficult to find out K. especially given the fact that we are doing the elliptical curve arithmetic over here. So the same reason, just like we had for LGAML as well as for the DH, the same logic applies over here. That's a trapdoor function and it's a discrete logarithm of complexity. That's why we are using it. Alright. Now see the process. Very simple. Let's see. It's another just a process that is involved and we'll solve a numerical also. So please see this carefully. This is all taken from Stallings because that is where it is like mentioned it properly. In case of carousel, it's a little complex in a way I feel. So this is easy. So first of all, we have to define through element. One is called as the global public element. Alright. So one is called as E cube AB. This is nothing but a representation of the function or the curve that we are all familiar with. This EQB is something like we all know E of 23, 3, 4. Just like we had done in our examples for elliptical curve. So same thing is represented over here. Naturally, you need to have a point Q, you need to have a point A and you need to have a point B. So that is being mentioned over there. So EQAB is the elliptical curve with parameter A, B and Q, where Q is a prime number or it can be also an integer of the form 2 to the power n. So if it is a Galois field, then 2 to the power n is 2 to the power 8, like that, and you can have that number as the value of Q as well. It's not restricted only to prime numbers, it can be integer, but it should follow 2 to the power n. Alright. Now this is one of the parameters. The second parameter is called as G. Okay. Now the point on elliptic curve whose order is large than n. So remember the n, I told you the order of n, that is where the limiting condition we are imposing. So this is ideally a point which lies post the n value. So if I go back to the curve, it's something like, if suppose a point lies somewhere over here, so the G should be a point like this, somewhere which is beyond the n. Alright, so these are the two public variant or the global parameter that we have to define. In most of the questions, this will be provided to you. Alright, so the curve E cube AB and the global parameter, the G part, will be provided to you. Now we come to the process of encryption. But as we have already discussed for LGAML as well as for the DH, we know that we need to find out the private key and the public key first, and then we have to send it with respect to the data or the main text, the plain text, and let's see how it is going to work. So the first step that is involved is user A key generation, like in the previous case also. So first of all, select a private key, which is denoted by NA. A is suffix to because it's for the user A. Alright, and the range will be NA should lie somewhere less than N. Just a condition. N is the order which you have chosen by some means, and NA should be less than that. Okay? That's how it is. That's how simple it is. So it can choose any value over there. So it is to be kept secret. So NA is there, and we have PA, which is the public key, which is to be shared, which we know for that matter up to now. So PA is given by the equation NA multiplied by G. G is the point that we have considered beyond N. So G is the global parameter which you have already considered, and NA is the private key which you have considered over here. So the public key has a component of the private key inbuilt in it. Okay, so that's one of the uniqueness of the system. So now this is about the key in the A direction, the transmitter side. This is what you are trying to do. Now the receiver side, we are going to do the same thing. We are going to take some private key NB, which again lies between this range, and we are also going to get a public key PB, which is again NB multiplied by G. Now this G is known to everyone, just like we have done in last class also. I told you the primitive roots or the generator will be known to everyone. The public key should be known to everyone. Prime number also will be known to everyone, except that the private keys will be unknown to each and every node. Other than the intended users, the private key should not be known to anyone. So here also the same procedure is followed. So we have PA and PB. Now let's try to encrypt it. Now you can see we are generating very similar to LGAML. You can see we are generating something called as K using the private key of A and the public key of B. Please make a note of this particular step, because this is where it becomes difficult, I would say, different to that of the previous ones. So we are generating a secret key for pi b. It is generating, there was a private key, there is a public key, but apart from that, there is another key which is generated at small k or capital K, whatever you call it, that is given by the private key of A, because this is generated at the A end. So A has the private key already. It takes the help of the public key of B and it generates Na multiplied by P. Similarly, B also generates K prime, and this is by taking the help of the private key of B, which he already has, and the public key of A, so PA. Based on that, you can see that the key exchange is completed, because if you check over here with the calculation over here, K and K prime should be equal. I've just given you the steps over here, it's a very simple way of logic. So this secret key that is generated at both the ends, apart from the secret key, so one, we have private key, the private key and the public key are generated first. Using those private and the public key, there is a second stage of key which is generated, and ideally both the side, this should be same. So that is being shown over here, that K and K prime are same. Now this K holds the key, this small k or capital K, I think I mentioned it's capital K. This capital K holds the key for the ciphering process. So let's see how the ciphering goes. Any doubt till this point? Anyone? Okay. Now, let's suppose the message M to be converted to a point form. Now, this is something very unique to this elliptical curve. Fortunately, we don't have to worry much over here and we don't need to discuss much. What we are looking at over here, see the statement, the message M to be converted to a point form, which is Pn. So, any given data, if it is in hexadecimal, if it is in binary or digit for that matter, it should be converted to some value of a point format. Point format means it should have an X, it should have a Y. Like it should be something like X, Y. But as I said, this is beyond the direction or the duration of the class which we have to discuss. So in all cases, your message should be provided to you in the form of a point. Am I clear with this? We don't need to convert anything, we don't need to learn anything over here. In all the cases, your message should be given in terms of a point itself. You don't need to convert anything. Okay? But this is a specific thing that we have to consider. Why? Because you will soon find that all the calculation we are going to do is in terms of the point format. Because we are dealing with a elliptical curve. The curve has different points. So we are having, if we want to cipher a particular data or a message, that also needs to be converted to that point format. Otherwise, the multiplication or the addition in elliptical arithmetic won't happen. Remember, in case of elliptical curve, P plus P, although it's an addition, but basically we were adding the 2 points. It has x1, y1 and x2, y2. So based on that lambda, we were able to find out the 2p. Remember that process. So here also the same meaning. The message is to be converted to some kind of a point form. And most of the cases, are rather in every cases, your message will be provided you in terms of point form only. So that's the first thing. Now, let's see about the CM. Please make a note of this equation. So the ciphertext CM, alright, is given by KG, comma, PM plus KPB. So this K is the one, it chooses a, you can see, chooses a random positive integer K to produce the ciphertext. This K that you are looking at, this is the secret key we are talking about. Alright, so this K, small k that you are looking at, this is being used over here. So the part of the cipher, remember in case of L-Gamal also, we had found C1 and C2. In last day's class only we did it. C1 and C2, two part of the ciphertext were used using two such keys. Similar kind of observation here. You can see there are two parts. One, it is used with respect to the global element, that is G. Remember, G is also a point. Okay, G is also a point. And here PM is a input message, which is a point, plus K into PB, where PB is the public key of P. So that's basically the ciphertext, but this is also in terms of a point representation. We'll see the numerical, it will clear your doubts. So, but for the timing, please make a note of this equation. So this is my ciphertext. So for the ciphertext, we require the message naturally, but we also require a small k, and we also require G and PB to be known to us. Everyone all at the same point, right? Okay. Now let's see the decryption. Decryption is of two types, two phases. But ideally, please make a note of this last one over here. So basically, I'll just do one thing. I'll just keep it this way. Now see what is happening over here. Pn plus kpb, the second part of it becomes the first part. For the decryption process of elliptical curve ECC, we call it elliptical curve system. Pn plus kpb, this is becoming the first part, and then it is subtracting kg multiplied by nb. So please make a note of this. This is a little difficult in a way. So one part is Pm plus kg. So the first part you can see B multiplies the first point of in the pair by B's secret key. So kg is multiplied by nb, and this whole thing is subtracted from the first part. So that will give you the Pm. In fact, bottom you will find that Pm is why we can find out the plain text back. We can see that, and I'll show you with the numerical also how we are going to do it. So first is that we have to make sure the secret keys are generated. Based on that, the ciphering should take place. All remember is in the point format. And after that, in the receiving end, we are going to utilize the same process, but there will be a subtraction that will take place where the first part will be, or the second part will be subtracted from the first part which is present with us. And we will generate the Pm. Let's take a numerical and let's see whether we are able to understand this. Hopefully all of you are having the equations with you, but let's see. I've tried giving as much as information possible over here. So the question is, there are three parts to the question. This is the first part. The crypto system parameters are given as E11, 1, 6. So the elliptical curve that we are working on is E11, 1, 6, and the global parameter G is given as 2, 7. Please make a note of this. Alright, so this is given by the two equations. So if you remember the first step of the algorithm, E, Q, A, B and G should be known to us. So that is provided to us. And this is the point format I'm talking about. The point format. Alright. And also B's secret key, that is NB, is given as 7. NB, the private key of B is provided by 7. Find B's public key, PB. Alright, because PB will be the equation I've mentioned over here, NB multiplied by G. In the steps itself I told you. Now the thing is, NB is given as 7 and G is given as a point. So basically here it is something like G into like this. It's happening like this. But if you observe here, this is nothing but a 7G. G is a point. If you go back to elliptical arithmetic, okay, if I go back, it's mentioned over here, but still, at that time also, P was a point, X, Y. And suppose we were trying to find out 2P. Remember the question that I given in class also and even in your CAT. So in 2P, what was there? It was P plus P, something like this we were doing. And if for that you require those lambda value, you leave that XR, YR. Remember the process. Same thing is applicable over here. You have to find 7G over here, which is nothing but, you can see over here, last line I mentioned, G is 2, 7. So you have to find what is 2G, which will come around 5, 2. Similarly, you can find 4G, which will be around 10, 2. Similarly, if you find 7G, it will be 7, 2. This calculation I have not done in the solution, but it is expected that you are going to do it in your exam. Because this involves the elliptical arithmetic calculation. This is nothing to do with the crypto system. Alright. So this is everything same. I think in the next page I'll let you know just to recap on what we have done. These are all the equations we are going to use. Is it familiar to all? This is all you have done, I think, in your CAT 2. So this is my XR, this is my YR, and these are my elements right now. Because here G7G means it's all P equals to Q. So you have to consider this equation, you have to form the lambda. You can see all the information is provided. I have already given it over here. As P is equal to Q. So we can find out that PB is coming as 7, 2. So this is the only trick involved with this ECC, that all these calculations will be done with respect to elliptical curve system. Please make a note of it. Don't just multiply 7 multiplied by g. It doesn't mean that the coordinates you just multiply 7 with. Like I'm telling you what I'm mentioning is 7 comma g, right? 7 comma 8 comma 2. Suppose this is given. And suppose you suddenly make something like 56 comma 14 and you say that this is the point. That's not the way to do it. It's just that this is an elliptical arithmetic because we are following an elliptical curve. So all the rules should be applicable. That's why in the second module when we were discussing about the arithmetics involved, I told you the properties of elliptical curve arithmetic. Okay? So 7g is what you are calculating over here and you are generating the point 7 comma 2. So this is my public key 7 comma 2. All in point format. See for yourself 7 comma 2. That's basically the point format. Now let's see the second part. Any doubt with this part? First of all, why we are calculating this? How to calculate 7g? What is the reference to it? All is given over here. You just substitute the data. It will take a little bit more time to solve it. That's the only point. Otherwise, it's same. Okay? Now, let's see the second part. Now, suppose the given question is, A wishes to encrypt the message. See, message is given in a point format. Message is given in a point format, 10 comma 9. As I said, you should be given a message in this form. You cannot be given any other way. So, message is given is 10 comma 9 and my random variable k, small k is given as 3. Question is determine the ciphertext. So, what is the formula for ciphertext? Small k into capital G, comma, PM plus KB. Very simple. Only the problem that you might have is the calculation. So, k, small k is 3. So, 3. G has already been defined as 2 comma 7 in the first case itself. So, K and G substituted. Your point over here is 10 comma 9. So, PM is 10 comma 9 plus K is 3 and PB is 7 comma 2 because you have just now calculated 7 comma 2 over here. So, you have substituted over here. But again, remember, all these calculations that you are looking at, they are all in elliptical curve. So, 10 comma, you can see I have given the steps also in between. So, this is 3 into G, 3G calculation. Everyone comfortable with this? This is nothing but 3G. You have to, it's like G plus G plus G. 3 G's you have to add up. So you find out what is 2G, 2G plus G. That should be giving you the value. So this 8 comma 3 is coming in because of this. Comma 10 comma 9 remained as it is. This is again 3 comma NB like this. Or rather PB. So this 3 comma thing again will give you 3 comma 5 over here. Remember again the same procedure as in the previous A segment I told you the same thing is happening over here. So we get the value here. Now we have P plus Q. See I have written over here P plus Q. Remember the process P plus Q is equal to R. So the same thing in that case we have to use the lambda as this. Because P and Q are non-equal. So we get another value which is 10 comma 2. So now we have this 8 comma 3 and 10 comma 2. This will be considered as my ciphertext. Am I making sense? What I mean? We are just substituting the data. The addition and multiplication are done as there is no multiplication in elliptical curve arithmetic. We have to do only addition. For the addition purpose, we know that we have certain formulas that I told you was there. We have to find XR, we have to find YR, but there is a lambda associated with it. Now the lambda value changes within whether it's P equals to Q or P not equals to Q. So in this case, as it is P equals to Q, we are using this formula. If it is P not equal to Q, we will use the other formula. Already you have done it in Cat 2. So all this way you are trying to find out these 2 points. See the ciphertext. It is in the point format. So that is the result of the message 10 comma 9 after getting ciphered to 8 comma 3 and 10 comma 2. Clear with the process? I know I'm leaving the calculation part to you because that is not that difficult I feel. It's just that you have to substitute rightly in that equation and you have to find out the points. Okay, so that is about this end. And finally, the question is, show how the message can be recovered back. That is, you are feeding the data, you have the data over here 8,3 and 10,2. You have to come back to the final result of 10,n. So that is given over here. In the same manner as kg into nb, we have to follow the steps as it's mentioned. So this is given over here 3g into 7. 3g can be calculated in the same manner, like you say 8,3. So this is given as 7 into 8,3. So everything I'm substituting over here. You can see I have marked this one 10,9 plus 3, this part already calculated. Where? Over here. Alright, this is just you can later on you can check it later. So you can just substitute 10,2 over here directly. One interesting fact will come in, which I thought of telling you, other than the calculation, is that you check here the step that I have marked over there 10,2 minus 3,5. So this is a scenario where you are actually doing P minus Q. So it is P minus Q you are doing. Can anyone tell me what exactly has happened over there or how we are going to do? It's P plus minus P. Remember, there is no subtraction in case of arithmetic. So what we have to do is, we have to take minus P over here. You can see I have changed it. 3,5, 3, minus 5. P and minus P, what was the property? If P is given by x, y, minus P will be x, minus 5. That's what I did. But since minus can't be acceptable, what we have to do? We have to take the mod of it. And we cannot take, like, it should be minus 5. Ideally, what is happening inside here? I'll just take a minute to solve this. So it is like minus 5 mod of 11. That is how it is going on. Now, minus 5 cannot be accepted as we know. So what do you have to do? 11 minus 5, so it's basically 6. So you have to take the positive of it. So you have to take 6 mod of 11. So your answer is 6, and that is why this is coming as 6. This step won't be there in anywhere. Don't worry. If this minus will definitely come. For any equation, minus will come. Whereas minus or subtraction is not there in elliptical curve arithmetic. What we have to do, we have to make plus. But we can do the plus only if it is minus P. Minus P as per the property is x, y. If it is P, then minus P will be x, minus y. So this 3, minus 3, 5 will be replaced by in between 3, minus 5. But as minus 5 is not the right way of doing any modular operation. So what we have to do, we have to take from the mod, subtract from the maximum of the mod. So 11 minus 5, we are taking it as 6. 6 mod of 11. So the answer is 6. So that 6 is coming over here. Now it becomes a P plus Q problem again. And P plus Q again can be solved in the same manner just like in previous case. We get the marks. I can understand the problem that you might all have is that the calculation part, because it becomes too lengthy, I feel, at times. So I would request all of you to please look into elliptical curve arithmetic, and especially the formulas, because you are not going to take your notes or anything. In CAT 2, you at least have a reference with you, but in term end, you don't have anything with you. So please make sure that you remember these two formulas, especially the lambda formulas for this kind of question, because it will help you in solving question in elliptical arithmetic as well as for this one, if at all comes in like that, right? So in all probability, this is the type of questions from elliptical curve arithmetic or key exchange is usually going to come. Right? Or maybe a part of it might come, whatever it is. But the process is involving elliptical arithmetic, so please be careful with that. That is my request. Don't do the normal addition, subtraction, all those stuffs. Okay? And in any case, if suppose you are asked to find all the points, suppose you are normally for elliptical curve, you can find all the points, find the whether it is satisfying the equation, those type of questions already I told you in CAT 2, right? This time that is another type. So that is one type of question based on elliptical arithmetic. This is the application of elliptical curve on cryptography. Alright, so this is how we are ciphering the data and we are getting back the data once. Okay? So that concludes our module 4 of key exchange techniques. So we have discussed the TH, we have discussed the LGAML, and we have discussed this one as well. Pseudo random, we are not doing it because we have already done the similar kind of thing in module 3 as well as module 2. So the same thing is there, so we don't need to waste much time on that. Okay? So let's start with the module 5 as we have discussed. Like I'll just go through a few things before we end up today. So module 5 is dealing with something called as hash function. Alright. So this is the module 5. This is relatively, I would say, different to what we have discussed so far. And what I have come across till now, this portion 5, 6 and 7 module, they are primarily a theoretical part of this subject. And you will find that very trivial kind of questions will come in from this part, numerical I'm talking about. It is more like a conceptual thing that will come in. Alright, so let's see whether we are able to understand them correctly. So this module 5 deals with two basic topics. One is called as cryptographic hash function and the other one is called as message authenticating code, or a MAC we call it. So let's see one by one what exactly are these things. So ideally what happens up to this point, what we have discussed is, we have discussed about the plain text, we have discussed about the key, and we are finding out that the techniques, be it a DES, be it an AES, this is trying to encrypt the symmetric or the asymmetric way. We are trying to hide the data and we are sending it. In fourth module, what we have understood that even when we are sending it, there is a way in which the key can also be exchanged from transmitter to receiver. And in the process that the intruder will not be able to understand the key has already been exchanged. That's all fine. So that makes the data confidential. We all agree to that. But now this module primarily discusses on the authenticity of the data. That whether the transmitter who has sent the data to the receiver is actually made the data authentic. Whether the receiver, when it receives the data, how will it know that it has come from the right source? So this segment discusses about some strategies which we have to append on top of the message. Sometime on top of the message, sometime on top of the encrypted message, be it. So using that process, we will try to authenticate that yes, the message which was transferred to you is actually coming from the right person. It is just a very simple example from where it actually came as an idea. If you say, suppose you have a will, okay, land will, the house and all, property will. Now suppose I make my own signature, or if I put a fingerprint on it, thumb impression. Usually still now thumb impression still goes on, in fact. And as you know, the thumb impression is unique to everyone. So we are making a thumb impression. Why? Because we are making that offline document, that hard copy of the document to be authentic. As long as it is, it will always remain that I am the user who has authenticated it. Confidentiality I am not considering at the point of time. Suppose I have made a normal will where I have given all the properties to someone. So that is nothing to confidential, that is nothing to hide. I'm not hiding the data. I'm just giving the data, but I'm making a stamp to make it authorized. I'm making it authorized. Like the way we do the digital signature. Right? Same thing is happening over here. So that is where this cryptographic hash function will come in and its properties will be utilized. So they have these properties in which the MD4 that you are looking at, that is where in 1990s, people started to have this digital form of authentication. So this MD4 led to SHA 512. 512 stands for the 512 number of bits that we are going to process once again and again. And finally, we have Whirlpool as a technique also, which is adopted in the same way. But this all technique deals with the same thing. One is how we are going to authenticate it. We are going to use it using some kind of a hash function. And after the hash function, the third part, this part, if you observe this part, will tell us how to make that hash function. Okay, so that's the topic for our discussion. So let's see about this one. This is already, I told you about the fingerprint thing, that for the integrity and the authenticity, we are going to take care using this process. So document and fingerprint, just now I gave you an example, so I think we can skip that. So please see this diagram for yourself. So what we are trying to do, the same thing as is adopted by a paper and a fingerprint, we are doing the same over here. We have a message document over here. And we will have some kind of a function which is called as hash function, which has some strategy, which has some property on its own, which will be on top of the message, and we will make this as message digest, or we will call this as a fingerprint, as like if you analogous, if you consider it to be a fingerprint, like we are authenticating it. So what will happen, we will send this, we will make this encapsulation, we will send it over the air. For the timing, let us forget about whether the key is exchanged and all those processes done. Supposedly it's all done properly. At the receiver will receive the data. It will compare the previous and the existing one, and they will compare the hash function. If the hash functions matches, we will say that yes, whatever the data was transmitted, we have received the same, or the source of the data is authentic. Am I making sense? Why we are studying this? All right. So you can see here the electronic equivalent to document and fingerprint pair is a message and digest. To preserve the integrity of a message, it is passed through an algorithm, and that is called as cryptographic hash function. The function creates a compressed image of the message that can be used like a fingerprint. That can be used as a fingerprint, and that has certain properties. So let's see. So this is basically what is happening over here. The plain text goes through some kind of an hash function. And after that, we have a fingerprint, or we have a fingerprint which is unique to that particular message. So even if suppose the intruder will have the message, okay, somewhere in between, suppose he gets the message over here, this message he gets, it's impossible to come back to find out the input message because the hash function is unknown to them. Okay, so that's how the authenticity is made. So you can see the two pairs, document and fingerprint, or the message and message digest, are similar with some differences. One is that in case of document and fingerprint, it is physically linked, but here there is no physical link, it is unlinked separately. Okay, so naturally you can see the message digest needs to be safe from any changes. Even one big single change will completely change the message digest itself. So it's very difficult to crack. Alright. Now, first of all, the checking integrity, as I already have told you. So this is my current digest. Suppose initially there is some kind of a digest which is present. Based on certain initial condition, we have found some digest. So for the timing, all of you should understand digest is nothing but the fingerprint. So we already have a database where the fingerprint is present. Now we get a current fingerprint. So we will match and we will say that whether it is matching. Just like in many of the web series, you will find fingerprint if it is matches with the crime. Well, same thing. So we have a predefined data set. From data set, we are matching the fingerprint. Same thing here. We have a previous image, or we are calling that as digest, and we are matching with the current image. If it is yes, then the message is not changed. If it is no, then message is changed. So you have to discard. And we have to go for a retransmission of the data. Right? Now we have three properties. Let us discuss this one by one, and that will be end of today's class. So we have three specific things that we have to consider for a proper cryptographic hash function. So the three properties primarily are pre-image resistance. Second one is second pre-image resistance, and the collision avoidance. So these are the three, as you can see over there. I don't think I have to repeat one. And they're very interesting actually. They have some very interesting properties. So let's see the first one, pre-image. So let's see the names once again: pre-image, second pre-image resistance, and collision resistance. Okay. So let's see the first one. So if you observe the animation itself, you can see it's very clear. So we have different set of input. If you see here in the left hand side, we will have different set of input, and we are generating the digest over here. All right. So see, hello goes in, it generates some kind of a digest. Then I love dogs comes in. That gives a different set of images. And the third one is the number goes in and it generates another set of digest. So for that matter, what it means is, you can see in the writing, this property means that it should be computationally hard to reverse a hash function. Which means that given a hash function h and y equals to hm, it must be extremely difficult for the intruders to find another message m prime such that y is equal to hm prime. That means for two set of input messages, the same hash function or the digest will not be added. Very simple. Me and him will not have the same fingerprint match. Same thing is given over here. Messages based on whatever it is, if you are getting it, it doesn't matter because you cannot do a reverse process and you can find the same message has delivered. There can't be two messages which will have the same kind of digest that will generate. So you can see this property protects against an attacker who only has a hash function or hash value and is trying to find the int. You can't. So that is one of the property that a cryptographic hash function should have. Alright, so that has been mentioned over there, that even with the hash function, it doesn't matter. You cannot go back and retrieve the data. Okay? So this is one first thing. Second part is, see, this is, as I said, this is just a block diagram. So the message comes in, raw message, goes through a hash function. That hash function generates some output which is y equal to hm, which is given as the digest. Now this digest goes through the channel. Okay. Now suppose Eve is over here, which is the intruder. He gets that hm. But from that hm, he is not supposed to find back what is m prime. He should not have m prime equals, it should have m is not equal to m prime. So if it is not, like the other case, if suppose with the hash function somehow is able to crack the message, then basically your cryptographic hash function has a problem with the pre-image resistance problem. Okay? So that's basically what the idea is for pre-image. So this is not the only property, but it is one of the necessity for any cryptographic hash function. So you will find the properties or the process that you're going to involve soon. You will all have this property inbuilt that we are considering, that it will have a good pre-image resistance, it will have a very good collision resistance, and a second pre-image resistance. So this is about the first one. Second one is also equally interesting, and that is given as second pre-image resistance. In that, what you are looking at, no hy is equal to hx. That means no two digests will be the same. Generated from two different inputs. Y and x here are two different inputs. Input x and input y. Same thing, just like we did in the previous image, very similar. It's like a dual protection to it. So even if you're getting an digest, same thing what I told you, hx cannot be equal to hy. It's an hypothetical scenario that for both two different inputs, we will generate a same kind of digest. So hx is equal to hy is not going to happen. So that is one of the another element of it. So you can see here, given an input and its hash, it should be very hard to find. It should be very hard means it is supposed to be. A cryptographic hash function will be such that it will be very difficult to find a different input with the same kind of hash. You cannot have. Okay, unlike you are watching a Happy New Year movie where Abhishek Bachchan's fingerprint can be used to open a locker. That's a different issue altogether. We have the same digest in that case. So this is basically the diagram once again, which I can skip for the time being, because this is the third one that we come across, and that is called as collision resistance. If you observe here what is happening, again, the property means that it should be hard to find two different input of any length that result into same digest. Me and my brother, okay, we should not have a same fingerprint match. It can't be. Right? So that's the basic property. You can see in the diagram itself, there are two different inputs given, but the digest is the same. So two different input cannot have a same digest that will be generated. So naturally that is easier. If that is the case, then basically retrieval will become easier. You can use the same digest and you can retrieve back the data, any one data for that matter. So this will not happen. So all these three properties should be maintained. In order to make a good cryptographic function, which is lie somewhere in between this Venn dash. Okay? Any doubt over here? Remember, for the time being, we are excluding the encryption, decryption, ciphering, keys being used, and all those stuff for the time being. We are mostly focusing on the authenticity of the data. So that is where our cryptographic hash function comes. So next day when we are coming back, we are going to see the application of cryptographic function, and we'll end up discussing the MD4 and SH512 most probably. Okay? Fine. So let me